So a parallel plate capacitor, you've learned, are two plates that are parallel to each other. And by plate meaning a sheet, it could be a disc, it could be a square sheet, it doesn't matter. The condition is that they're really large compared to maybe the dimensions we are looking at inside. Okay. The other condition is one of them is positively charged and the other one is negatively charged with the same amount of charge. Okay. They also have an area A. They each have an area A. And from that we know that the electric field inside a capacitor, which I use a subscript C, is a constant. And that's the most important thing about a capacitor. That's one of the most important electric fields we know of, is the electric field of a capacitor, because it's constant, and it's given by Q over A over this constant epsilon 0, which is 8.85 times 10 to the negative 12 in the proper units to convert. Okay, but the most important thing is to recognize that it is a constant. It doesn't get smaller with distance or bigger with distance. It has no distance dependence, so no matter where you're at, it's constant. And so we can use that as a really powerful tool for controlling the motion of charged particles. And it behaves and is analyzed just like throwing a baseball. So for example, what if I take a proton, and I'm well within the capacitor, I take this positive charge, let's say it's a proton, and I shoot it with some speed v0, okay, I shoot it with some speed horizontally or along the gap of the capacitor. What's going to happen to its motion? Right? Well, we know that electric fields point away from positives and towards negatives, so I know the electric field everywhere in here is this direction, okay, and it's constant everywhere. Well, acting on a proton, the proton will follow that electric field. We could also have seen that the proton will be repelled from this positive plate and attracted to this negative plate. But I asked, is there any force that's making it go left or right? And the answer is no. The electric field is pointing straight down, and the forces are always always parallel to the electric field. And so this is just like throwing a baseball horizontally over the surface of the Earth. There's a downward force of gravity, and it will curve in projectile motion. It will have a parabolic path. And so I can ask all sorts of questions about this. I can say, okay, if I know the speed, and I know how high I launch it, so I give it a y0, well, where would it land? Okay, maybe x1. Okay, I could say how long is it in flight, or I could say how big does the charge need to be in order for this to just barely hit inside the capacitor. I could ask all sorts of relationships to compare these two. So let's just throw some of those ideas in equation form and try and make sense of it. First, we can see that we have a kinematics problem. So I'm going to redraw this. I'm going to draw that positive charge here, and then it's down here. Okay, I'm going to draw a coordinate system. Here's x, here's y. Okay, I'm going to list t0, an x0, a y0, a v0x, and a v0y. It's a two-dimensional problem, so I have all those possibilities. At their final state, I have t1, x1, y1, v1x, v1y. And then everywhere in between, I'm going to have some acceleration, and I know it's down because of my knowledge of how it's repelled by positive, attracted to negative, or that positive charges follow electric fields. Okay, the force on a positive charge is in the same direction as the electric field. So the kinematics just assumes an downward acceleration, but the dynamics, the forces, is connecting that acceleration to the force. Okay, so with that in mind, we can just relate these things. I need to get a free body diagram here. So here's a free body diagram with we have the force is downward. Okay, so this is going to be F sub c, the Coulomb force. Okay, that's the Coulomb force, and that's the only force, which means my acceleration is downward. Okay. So that's sufficient there. And now I can start relating things. Well, so first of all, my acceleration that I need, I'm going to call it AY, is going to be equal to F net Y divided by M. Okay. So I'm writing Newton's second law this way, so I'm trying to make that explicit connection to AY. And looking at that, that is going to be equal to Fc over m, which is equal to E times Q of the proton. I'll put Q plus, emphasizing the charge of this proton. Okay, and that, maybe be more specific, that's m plus, that's the mass of that proton. Okay, well with that in mind, I can plug this in for E, and I have a relationship that relates A to these parameters that I either know or could find. So I'm just going to pause on that now. I have that information with those two. And lastly, I can come over here and try and figure out some kinematic values. And so this is just a standard kinematic problem once I've figured out this acceleration from Newton's second law and the field of a capacitor, and I could calculate. So let's go and be explicit. Let's say I know how fast I shoot it, okay, and I shoot it horizontally. That means v0, y0. My coordinates say this is 0, and let's say I know how high up I launch it from, so I know y0. And I can always choose my time, so that's 0. Okay, and let's just ask, I want to know this one. I want to know where it lands. And I do know this one because that's at 0. Okay, so writing my list of knowns for this. T0 equals 0, x0 equals 0, v0, x is something I know. I'll just not put a number, but say it's something I know. Okay, my y0 is something I know. Okay, I give you that value, and explicitly v0y equals 0 because I launch it horizontally. Okay, my AY I can find from this information over here. Alright, so what am my y1, I know that's 0. I don't know my velocities, it's still moving right before it hits. But what am I trying to find? I'm trying to find x1. Okay, in order to do that, I need to find AY. Okay, and from that, I actually need to know the information from Newton's second law. So I need to know the Coulomb force. So I'm going to put that in parentheses, emphasizing I need to kind of find that. Okay, so because of that, let's assume I know Q, I know A. So that means I know this, and I already know the mass of the proton. Okay, and I also know Q of the proton. That would be in the front cover of the book, or you can look that up. So these are all the things that I know to find. I find AY through Newton's second law and through the electric field of a capacitor. So we'll just go ahead and assume I now know that. And then finally, I just need to find x1 now that I know the acceleration. Well, let's see, what do we have? I know about my y positions. I know the initial y position and the lower y position. So if I look at the y, I could say that y1 equals y0 plus v0y t1 minus t0 plus 1/2 ay, and I'm running out of room, so I'm going to put delta t squared. Okay, and my delta t is just t1, so t0 is 0. But I also have v0y is 0, and my y1 is 0, and so I can find my time by, here I have my t1, I'm going to subtract this over, so I get negative y0 times a 2, multiply the 2 up, divided by ay, and then square root it. Okay. Now note, my ay is negative, and so the value I get from here, I would plug in a negative value there. So I have that one, and now finally I would need to plug that in to find my x position. So I know my initial x position, and I know my initial x velocity. So if I do x1 equals x0 plus v0x, I'll just do delta t again, plus 1/2 ax delta t squared. Well, I know it's not accelerating in the x. Okay, I've chosen my initial position to be 0, and so now this just equals v0x, which I know, and t1, delta t is just t1 because t0 is 0. And I just found that here. So let's review this really quick. So first of all, we understood that the electric field of a capacitor is constant, and therefore the force is constant, and therefore the acceleration is constant. Okay? And because of that constant acceleration, we could then use our kinematics for constant acceleration, as we did down here, and just carefully step through it. We first found AY through Newton's second law and the knowledge of the electric field, and then use kinematics first in the Y to find time, and then in the X to find the overall final position.